bullet is fired into a liquid with an initial velocity v0 at an angle theta from the horizontal. The liquid causes the bullet to decelerate proportional to the velocity of the bullet, and we're asked to find the x and y components of the velocity, and also what its terminal velocity is. Well, basically, the bullet will have a rough trajectory, something like this. It'll fly up and probably fly down due to gravity being its long-term influence, and it'll be something like this. I don't actually know the equation of motion yet because we need to work it out, but it'll look something like this. And not only that, but at time t is equal to 0, the bullet flies with initial velocity at an angle theta, and at some time t, some arbitrary time t, I'll draw it just here, some arbitrary time t, I'll just draw that right there, at t is equal to t, it will have a velocity v of t, it will have an acceleration due to gravity, which I'll call g, which is just a constant. And not only that, but there will be an acceleration due to drag, which is this acceleration we were talking about earlier in the question, which is going to be opposite to the velocity. It's going to be a vector which is parallel, but negative to the velocity vector right there. And I'll call that AD, just there, to denote its drag. And we're told that the acceleration, or like we're told to assume that the acceleration due to drag is going to be proportional to the velocity of the bullet. Right? In other words, that means we can just simply write that our acceleration due to drag is going to be equal to our proportionality constant, which I'll just draw as k, times by our velocity. Right? So essentially, what this really means is that our velocity vector is always going to be tangential to our equation of motion, and our acceleration due to the resistance of the fluid is going to be pointing in that exact opposite direction. I hope that kind of makes sense. Just like imagine running into the wind or something like that, and the wind, or in this case our fluid, is going to be pushing opposite to the direction you're running in. So I hope that makes sense. Now the easiest way to begin solving this is to group every single vector we've got here into its x and y coordinates. So if I were to draw a larger picture of what's going on down here, you'll have a bullet like this, and it's got a velocity vector v of t, and it's got its horizontal and vertical components with it as well. And I'll just draw that as v of, I don't know, I'll just call this vy, and I'll call this vx. And also, it's got its component of gravity, which is perfectly pointing downwards, which is already simplified enough. It's already been split into its vertical and horizontal components. It's just downwards entirely. And not only that, but we've got an acceleration due to the resistance of the fluid. I'll just draw this as AD, just here. And that can also be split into its horizontal and vertical components too, which is going to look something like this. So this is going to be this is going to be ADX, and this is going to be ADY. Okay, so essentially what I've done is I've just redrawn everything that's happening at this bullet at some arbitrary time t, and I've re-summarized it in terms of its vertical and horizontal positions. Horizontal and vertical components. So what we have to do now, call this a good hunch at the moment, but I feel like what we should do is we should express the acceleration of the bullet in terms of its net effects acting on it. So basically, we need to figure out what is the acceleration on the bullet in its horizontal component, and what is the net acceleration of the bullet in its vertical component. So, in other words, find out what AX is equal to. And AX is just going to be equal to the sum of all the accelerations acting on it in the horizontal component. Well, velocity isn't an acceleration, so we can exclude this at this point in time. But g is acting downwards, that's got no component in its horizontal, and ADY has no component in the horizontal direction. The only component is ADX just here, right? So we can write that as AD x with a minus out here too, because it's traveling left where I've defined positive as right. Right? Notice that these axes are positive facing upwards and positive facing right. So if something's traveling to the left, that means it's negative. Alright, so what about AY? Well, AY is going to be the sum of all the accelerations acting on it in the vertical component. Well, G is going to be negative because we've defined positive as upwards. And ADY is going to be negative as well because we've defined positive as upwards as well. So that's just going to be negative ADY subtracted from G. Right? So let me make this very clear. So the sum of all the accelerations acting on the vertical component of the bullet is going to be equal to the vertical component of the acceleration due to drag plus the vertical component due to gravity, which is both negative in these cases. Right? This is our starting block right here. These are our starting equations. From here on in, it becomes purely algebra. So in fact, let me just draw a line straight down the middle so that we can just separate these two equations right now. Let me just scroll down a little bit. Done. Okay. So we know that our acceleration at some particular point in time t is going to be equal to our change in rate of velocity at that particular time. So our left-hand side can be written as dvx dt is going to be equal to, and the right-hand side remains unchanged, it's going to be minus a dx, right? Notice that it's vx here because this is ax, so basically the acceleration in the horizontal component is going to be equal to the change in rate of velocity in the horizontal direction as well. Well, now let's figure out what the right-hand side is, now that we've sorted that out. So I'll just rewrite the left-hand side as the exact same it was before. But the right-hand side, remember, we discussed earlier that the acceleration due to drag is proportional to our velocity, so we can rewrite minus a dx as minus k vx. Right? So notice the vx is on the left-hand side and the right-hand side. This becomes a matter of algebra at this point. So what we could do is we can solve this properly by perhaps guessing a solution, but it's much easier to just solve this ODE because it's a simple one. If what we can do is we can multiply both sides by dt and divide vx by both sides, and I'll show you why that would actually help. If we multiply both sides by dt, we get dvx is equal to minus k vx dt. And if we divide both sides by vx, then we get 1 on vx dv is going to be dvx, I should write, dvx is going to be equal to minus k dt. And if we choose to integrate both sides with respect to, if we chose to just integrate both sides, right, we've already got our dt's and dv's on each side, then we can just solve this right now, keep knowing that our left-hand side just has vx's on the right-hand side, on the left-hand side, and our right-hand side just has t's on the right-hand side too. So this is already fairly sorted. We know that 1 over x dx is just log of x, so this will just become log of vx, and the right-hand side is just going to be minus kt, right? Because k is a constant. And don't forget our constant of integration outside as well. Well, we also know that at some particular time t is equal to 0, remember at t is equal to 0, our initial velocity was v0 at an angle theta, right? So what I'm going to do is I'm going to redraw this simple trig v0, this is at time t is equal to 0, it's going to have vertical and horizontal components as well at an angle theta. So this component will be v0 sine theta, and this will be v0 cosine theta, and that's at t is equal to 0. So at t is equal to 0, we know that our velocity in our horizontal component is going to be equal to v0 cosine theta, right? So if we just plug this in right now, we can simply write that log of, if we sub this point in right now, we can go log of v0 cosine theta is going to be equal to minus k times by 0 plus c, which implies that c is simply going to be log of v0 cosine theta. Now we plug all this back into our original equation just here, and we get log of Vx is going to be equal to minus kt plus log, because now I know what c is, I can plug it in, log of v0 cosine theta, right? Well, now if we were to group the logs on both sides using log laws, we can write that as log of Vx subtracted from log of VO cos theta, which is going to be equal to minus kt. And if we power both sides with respect to e, the logs and the e's cancel out, and we're left with Vx on V0 cos theta is going to be equal to minus kt, e to the minus kt. We powered both sides with respect to e, minus kt, and that will give us Vx, which is our direction, which is our velocity of our particular bullet at some particular time t, is going to be V0 cos theta e to the minus kt. Alright, that was a little bit of work, but I'm glad we solved it, because this has given us an equation which shows us our velocity of our bullet at any particular time t, and that's half the question done. So now we need to sort out what our acceleration is in the y component too. Let me just separate it right here. Well, we also know it's going to be the same type of formula. We're just going to replace ay with dvy dt, and the right hand side is just going to be minus k v y minus g, and remember g is just a constant. And once we solve this, what we could do is we could separate these equations as best we can. So if we were to, let's see, what's the easiest way to do this? We could divide both sides by the right hand side and multiply both sides by dt. So we could write this as, actually let me have a little bit more space, we could write this as 1 over k vy plus g, if we just divided both sides by k vy plus g, and that's just going to be dvy. And then if we multiplied both sides by t in that same step, then we're left with minus dt. Right? So what I've done is I've divided both sides by positive k vy plus g, and I've divided by that, and I've multiplied by dt. And now it becomes a matter of integration. So if we can integrate both sides, ta-da and ta-da, then we're left with, and let me just make a little bit more space here, then we're left with this. Well, this becomes a pretty standard problem right here. What we need to do is we need to find out a way to integrate this problem right here. Well, let me just remind you of a little bit of integration laws. If we're left with f dash of x over f of x dx, then that's simply just going to turn out into log, sorry, no integral, that's going to be log of f of x plus c. Right? That was derived in your math class. I won't go into a proof of that, but that's just the formula. So what is the integral, what is the differential of k vy? Well, it's kvy plus g. It's just going to be k, right? Because g is a constant, it gets eliminated. So we need to make this a k somehow. So we can rewrite the left-hand side as 1 on k integral k kvy plus g dvy is equal to the integral, I won't solve the right-hand side yet, minus dt. Right? Notice that I haven't really done much. All I've done is I've multiplied and divided the left-hand side by k. I could easily cancel this out. K divided by k is 1. So this doesn't actually seem like a step, but it's really important because now notice how the numerator is actually the derivative of this denominator. So we can solve this. We can say that the left-hand side is just 1 on k. That remains outside. Log of k vy plus g is going to be equal to minus some constant, because this is no t's in it. It's just a minus 1 right here. So it's just going to be minus 1 times by some constant, which I'll write as minus c, right? And as a result, you're left with sorry, no, it's not going to be minus c. It's just going to be minus t. Whoops, minus t plus some constant c. As a result, we can figure out what the constant is based off this information which we had just over here. I hope this isn't confusing you, having like so many different equations scattered throughout the page, so I'll just box them off a little bit. So remember, v0 was our initial starting point, so this is when t is equal to 0. We had v of y, which was equal to v0 sine 0. That was the simple trig based off our initial conditions. Sine theta. And what we're going to do is we're simply going to sub in this point to solve out what c is in this particular case. And if we do that, we'll be left with 1 on k log of k vy plus g is going to be equal to, well, minus 0 plus c. So in other words, we can say c is equal to this beast right here. I won't rewrite it for you, but I will do the next step for you. Now what I'm going to do is I'm just going to end up plugging c back into this equation now that we've figured out what it is, and we're going to be left with 1 on k log of k vy plus g is equal to minus t plus whatever our c was, which we calculated was just this left-hand side right here. Oh, and vy in this particular case should be v0 sine theta. Sorry for missing that step. That should be v0 sine theta. Remember, we subbed in t is equal to 0, and we subbed vy is equal to v0 sine theta. So c in this case is just this left-hand side beast right here, which is going to be 1 on k log of k, I'm running out of space, it's crazy, v0 sine theta plus g. Whew, this is turning into a long equation. Alright, but bear with it, it's almost done. So what I'm going to end up doing is I'm just going to subtract both sides by one of these logs, and then I'm going to multiply, then I'm going to power both sides with e as a base. So what I'm going to do is I'm going to subtract this one to the left-hand side. I'm going to write, and I'm going to factor out the 1 on k. So that's just going to become 1 on k log of k vy plus g divided by, because remember, a log subtracted from another log is just a log, and those subtracted are just divided. In fact, let me write that as another math law just here so I don't confuse you. Log a minus log b is going to be equal to log a on b. So that's exactly what I've done. I've subtracted this one from both sides. Is going to be equal to k v0 sine theta plus g is going to be equal to minus t. So that's a little bit more simplified, but it's not as simplified as it could be, because if we multiply both sides by k, we get minus kt here. I'm not going to write out this step. And if we power both sides with e, we can get the logs and the e's cancel off, so we get k vy plus g over k v0, which is our initial velocity, sine theta plus g is going to be equal to e to the minus tk. Alright, so we're almost done, we're almost there. What I'm going to do now is I'm just going to multiply both sides by this denominator, and then I'm going to subtract g and divide by k to leave you with vy just here. This is just purely mathematics. I'll try and make this video a little bit faster because I don't want to lose you guys. But if we were to do that, we'll be left with vy is going to be equal to k v0 sine theta plus g times e to the minus tk, and then that's going to leave us with this this bit on that side. So I'm going to subtract from g and divide by k, and that will be our answer right there. So I did like maybe 3 steps in that one go, but what I did is I multiplied both sides by this denominator, then I subtracted both sides by g, and then divided both sides by k to leave vy isolated on the left-hand side. And let me just simplify that one more step further just to make this a little bit more clear, because I've noticed that there's a k in here. So I can rewrite that as v0 sine theta plus g all times by e to the minus tk minus the ratio g on k. So this will be your component of your velocity of your bullet in the vertical direction. Whew. Alright, so now we've got our horizontal and our vertical components just here. That's one part of the question done. They also ask us what our terminal velocity is. Fortunately, this shouldn't take too much longer. Remember that our terminal velocity is the velocity of our bullet as time approaches infinity. So, in this particular case, I'll write this as tvx, terminal velocity of our x component, is going to be equal to our limit, our limit of v of x as t approaches infinity, which is going to be equal to, well, let's explore what happens here. There's no other components involving time except this e to the minus kt, and we know that e to the minus kt approaches 0 as t approaches infinity. You can test this on your calculator if you don't believe me, but e to the minus like maybe 4 million or something like that will be a really, really small number. So this will approach 0 just here. So that's our terminal velocity in our x component. What's our terminal velocity in our y component? Alright, this is terminal velocity in our y component is just going to be the limit as t approaches infinity of our vy, which is going to be equal to, well, we know that this left-hand component just here is going to diminish to 0 just like it did before, because e to the minus tk approaches 0, and none of this is a function of time. So this is going to be 0 minus, and there's no t's in here, so we're just left with this strange constant at the back, minus g on k. So in other words, our terminal velocity vector is going to be equal to 0 minus g on k. And that's our solution. Our terminal velocity vector is 0 minus g on k, implying that, and let me make this a little bit more clear, if we had our tank like so, and we had our rough path drawn like I did before, what I'm saying is as time approaches infinity, pretty much the bullet will be flying downwards only. As time approaches infinity, it will be going downwards only at a velocity that approaches g on k. It'll fly downwards because there's a negative sign at a velocity which is approaching g on k. So that's the solution. I hope that makes sense to you guys. It's a little bit tricky. Most of it was purely mathematics, but the most important part I'd say is realizing the free body diagram just here and splitting the components of each velocity and each acceleration into their horizontal and vertical parts. Oh, I hope that makes sense. Cheers.